Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very happy to have Avradip Mandal here to give the crypto colloquium. Avradip is a student at the University of Luxembourg, advised by Jean-Sébastien Coron. He works on a lot of very interesting stuff in crypto, including hash functions and differentiability. And more recently, fully homomorphic encryption. He'll tell us about fully homomorphic encryption over the integers with short error public keys. Okay.
Thanks, Vinod, for the introduction. So today the talk is about fully homomorphic encryption over the integers and with shorter public key. And by shorter, we mean this time actually we can implement it. Not really efficient, but we can do something anyway. So this is a joint work with Jean-Sébastien, David Nakash, and Mehdi Tiboshi. So, okay, so in the whole presentation there will be lots of nested equations, but at least I hope I'll be able to convey the basic message. So by homomorphic encryption, we mean it's an encryption scheme when it supports the operations on the encrypted data. So we have the RSA, which is a multiplicative homomorphic encryption scheme. So given a ciphertext C1, which is M1 to the power E, we can just try to get the encryption of C1, C2. And we also have the additively homomorphic scheme due to Pylea. So over here also, just if we multiply the ciphertext, we can get the encryption for the message M1 plus M2. And for fully homomorphic encryption, we mean it should support both addition and multiplication and as many times as you want. So it was an open problem until Gentry's breakthrough results in 2009. So over here we restrict ourselves to the encryption of bits, only 0 or 1. So when you encrypt the bits, it will get a big ciphertext, and with fully homomorphic property, given E of B0 and E of B1, we should be able to compute E of B0 XOR B1 and also B0 and B1. And not only that, if it is fully homomorphic, if we have a circuit with XOR gates and AND gates, given the input bits in the encrypted form, one should be able to compute the output bits in the encrypted form without knowing the private key. So this is some application of fully homomorphic encryption. Suppose we have a software, so that given your past income, past revenue and income and all the sensitive information, it can predict the future stock price of your company. But of course, I don't want to give you my sensitive information, and the guy who has the software, you don't want to give me the software. So how do we do it? If we have homomorphic encryption available, I can encrypt all my inputs using fully homomorphic encryption, and you have the software. You can process my inputs with viewing viewing your software as a circuit, and then you send me the result in an encrypted form, and I will get back my predicted stock price. So this is just one application. There are tons of applications if we can build a efficient fully homomorphic encryption.
Is it possible that with sufficient amount of data and I ask many times, I can guess what your formula is?
Well, if you ask a sufficient amount, that means...
1,000 questions, please do prediction for this 1,000 times. and you do the prediction, and from the result I get, I can try to guess what your prediction formula is.
Oh.
Yeah, of course you can, right? The circuit is very
yes,
simple.
you can
always learn what the
for,
circuit is, right?
for the circuit you may be able to, yeah.
Just getting the input-output. Well, it's equivalent to getting the input-output access. If you can learn from input-output access, then
Yeah, of course. So you can't say it's private. You can only say it's private under certain conditions on what the circuit is when you say it's not.
Yeah.
These are just inherent to all this SME multi-party computation.
So, Gentry scheme in stock 2009, that was the first fully homomorphic scheme. So it was based on lattices. And recently in 2011, Gentry and Halevi, they have given a implementation of the scheme, and they have the public key size as around over 2 GB and ciphertext refresh time around half an hour. And also in 2010, by Dijk, Gentry-Halevi and Binod, we had one a fully homomorphic encryption scheme, which was much more conceptually simpler. However, the performance was not better than the Gentry scheme, and it was still impractical. Public key size was more than 2 to the power 60 bits. And main selling point of that result was it was really simple to understand compared to the other the previous result. And in our work, what we do, we show how we can reduce the public key size in this simpler scheme over integers, and our implementation results are now actually comparable to the implementation by Gentry-Halevi of the original homomorphic scheme. And in fact, from the results, our implementation results are a little bit better, but still we can of course compare because security levels and those are completely different in two problems. So this is the DGH scheme from Eurocrypt 2010. To generate, for key generation, we have a set of tau public integers. And what we do at first, we generate a odd integer p and keep that as a secret, and then we as public key we output pqi plus ri. Q's are Q is generated randomly, so the p is secret and pqi plus ri is your.
How big or?
Sorry?
What properties do you need from the QI?
So QAs are they're in integers, I think, or maybe they're odd. Yeah.
Random integers from.
Random integers, yeah.
Well, it depends on whether you want an insecure scheme or secure scheme.
No, but there has to be a count, right? Otherwise you can't.
So this, if the size of P is 8 bits, we need Q to be more than 8 squared bits to not be insecure.
Yeah.
So if we have to 8 squared, then that's the group you're going to
So
select.
that's right.
Yeah, we will see about the security, like the parameter shortly. So this is the scheme, if we intuitively. So we have a set of x size as a public key, and so size of p is zeta bit, size of xi is gamma bit, and size of ri is rho bits. That's what our convention. So if you want to encrypt a message 0 or 1, we just choose a random subset S of 1 to tau and a random integer r, which is another secondary noise parameter in some other interval, and we encrypted as C as m plus 2r plus twice summation over x size, where x size are taken from our random subset. And to decrypt the C, all we need to do is just take C mod P and then mod 2. Now, noise in ciphertext is R prime, which is R plus sum over Ri. And for correct decryption, we always want this noise to be less than P. The decryption works as you are taking mod P as long as the noise is less than R prime P. I think it's the prime odd integer. So, for homomorphic addition, we just add C1 plus C2 and take. So, everything works as long as our noises remain less than P. So, R1 plus R1 prime plus R2 prime should be less than P, or R1 prime plus multiplied by R2 prime, it also should be less than P. And the important point is noise grows with every homomorphic addition or multiplication, and more in multiplication than addition. Yeah.
So when you say C is M plus 2 R prime mod P, it's not, you're not saying that it's a number smaller than P, right? So, I mean, so because you don't know what P is, so definitely.
Sorry.
So when you say C, so the C here
is
different from the C in the previous slide, right? So if you show the previous slide.
Yeah.
So here when you say, right, so the C here is M plus 2 times some noise, plus a multiple of P. So that's what you mean by.
Yeah, so that's not equal, so that's like and that's true in like modulo. Yeah, sorry about that. So everything should work as long as our noise remains less than P. So because of that, our homomorphic operations becomes limited. So this is this scheme what you call somewhat homomorphic scheme. Now it then comes the Gentry's technique. We start from a somewhat homomorphic scheme, which can allow only a polynomial of small degree, and with that, if we apply Gentry's technique, we can make it some fully homomorphic. So first step would be to squash the decoding procedure. So what do we mean by that? So that the decryption circuit, we should be able to express that as a polynomial of low degree, and the low degree should be lower than the homomorphic operation we are supporting. So this is the ciphertext refresh procedure. Over here, maybe. So we have the ciphertext bits and secret key bits, and the decryption circuit gives us the plain text. And as this is a somewhat homomorphic scheme, if we replace this ciphertext by encryption of the ciphertext bits and this secret key by some encryption of secret key bits, here we should get encryption of plain text bits. That means instead of this ciphertext, we will get another ciphertext. And why this is important? This will actually help us to reduce the noise. So the problem was before, if we are doing more multiplications, the noise was growing, and with this ciphertext refresh procedure, we can again make the noise less. And if we and that would mean if we have this, then we can do we will have a fully homomorphic encryption. Whenever noise is growing, we will just refresh the ciphertext once again. And so to make this work, of course, we need to make this thing public. Otherwise, the like if we don't have the encryption of the secret key bits, we cannot do the refresh procedure.
So what's the size of that circuit?
The size of the circuit?
Yeah. So you have to make use of the homomorphic property of your encryption scheme to evaluate.
Yeah. So the condition is the size of this circuit should be somewhat less than
Thresholds.
yeah, less than our threshold. Yeah, and it should be at least, if you want a multiplication to be done, it should be at least half of the threshold.
Do you have a sort of numerical sort of give me an idea of what's the depth compared to your threshold? In other words, how many?
Okay, so I think depending on the security goal, I think normally what we have implemented, we are getting this decryption circuit is a degree 13 polynomial. 13.
13.
Yeah. 13 or 15 maybe. Yeah.
Does the noise change with the parameter? How much noise can you tolerate? Does it change with your security parameters?
Yeah.
So
So the noise we are adding ourselves, right? So it depends on it depends on the scheme. How much it's all in the design. How much noise we are allowing.
you can actually increase the degree or the degree of the polynomial that you can support depending on the parameters.
Yeah.
But at some point it might become
Yes.
secure, right? If the noise is too small.
Yeah, but I can basically play with it.
Yeah, you can play.
Any decryption circuit I want, right? That's
Yeah.
And there is a strange cyclic dependency. So, if the degree of the decryption in the polynomial is small enough, the resulting noise in the new ciphertext can be smaller than the original ciphertext. And for fully homomorphic encryption, given two refreshed ciphertext, one can apply again the homomorphic operation, and which was not necessarily possible on the original ciphertext. So the ciphertext refresh procedure basically reduces the noise. So this is the constant on the parameters from the DGH paper from Eurocrypt 2010. So this is for around 80 bit of security, I think. So we need the row noise should be at least 37 bits, and over here the squash scheme has a decryption polynomial of degree 30, and we must allow for an additional multiplication, and we need some more 8. Yeah.
So if row is 37 bits and I can guess it, and I can break it in time 2 to the 37.
Yeah.
Right. So why do you say it's 80-bit security? I mean,
Oh, sorry.
By 80-bit security?
Yeah. It's not 80. So that's sorry about that.
So 76 is not enough, 77 is the right number?
No. So yeah. So even for that, we need the public key size in the end. It becomes like 10 to the power 14 is around 2 to the power 45 bits.
Initially you said 10 to the 60, now it becomes 10 to the 14.
No, initially I said 2 to the power 60, but it should be at least this one.
Oh, so 10 to the 14 is roughly 2 to the 60, sorry.
10 to the power 14 is 2 to the power, it should be for 45 or something, right?
So it's unrelated to the 2 to the 60 that you put before?
No, but this is, at least it should be this one. This is the basic attack. So, this is the internal security parameters. Row, the size of noise should be lambda bits, as we know said, and row prime is the secondary noise. It is 2 lambda bits, and the size of p is lambda square. Size of xi becomes lambda to the power 5, and the total public key size in the end becomes lambda to the power 10. And in our work, we reduce it to lambda to the power 7 in the end. So this is the basic idea behind reducing the public key size. So before we were doing the encryption using a linear form of the elements in the public key. So over here, instead of the linear form, we will use a quadratic form. But of course, using that, we will get more noise. But yeah.
So the size of the ciphertext is going to be the same. It's only the public key that's shrinking, right?
Yeah. So we start with a beta pairs of numbers xi0 and xj1. Now we can define beta square integers by multiplying them together. And now we will encrypt using a linear combination of those beta square numbers. So it's the, and also before we are taking the coefficients, either they are 0 or 1, and over here we will take it as a linear combination of all the elements in public key. And in fact, now we can take beta as lambda square. So that would give us public key size as lambda to the power 7. So now this is what will happen for the basic scheme. And now we need to squash the scheme. By squashing, we mean we need to make sure the degree of the decoding circuit that's less than the homomorphism we are supporting. And for that, what we are doing with all these is basically along with the ciphertext, we are passing a hint about the secret key. And that so public key over, okay, maybe we better go inside these ones. So for the key generation, initially we take some so initially we take xp as 2 to the power kappa by p, and then we generate a random theta bit vector, and so in the end what we are giving as a public key is another vector, instead the pk star what we are giving before, and another vector y, such that with the y there is some secret information 1 by p that is embedded in the y. So we are giving some more hint about the public key, about the secret key in the public key. And yeah.
In the previous slide,
yes,
right? So rather than have a bunch of numbers in the public key and take linear combinations to do the encryption, you're saying I'm going to have a square root as many numbers,
yeah,
and then I'm going to sort of generate these.
Yes.
Mental experiment, generate these numbers, and then I do it.
Exactly.
But then the new numbers, the smaller set of numbers, need to have smaller noise.
Yeah, exactly.
Right?
That's true.
So therefore, your security parameter has to be larger to accommodate.
Yeah, that's yeah. So, but again, we can play with everything. For that, we need to go deeper. But that's true. If we are making that, the noise will grow. So for the squashed scheme, so what becomes the advantage is the decryption function now can be expressed as a polynomial of low degree in terms of ciphertext bits and the secret key bits, and this allows bootstrapping and the public evaluation of the decryption circuit homomorphically. So the public key size in the DGHB paper is still over here kappa we have to take lambda to the power 5, and in the squashed scheme we are giving additional theta elements which are each an encryption of each is lambda to the power 5. So over there the public key size will be lambda to the power 10, which is okay over here. But in our case, if we do that, we will again go to lambda to the power 10 boundary. But actually we can show that parameter theta, we can make it lambda cube. So we will still get lambda to the power 8 instead of lambda to the power 7 that we are hoping for. So, and the theta was over here as a hint, we are giving a vector of length theta, and that we are keeping as secret key, and in the public key we are giving this yi, which is ui by 2 to the power k, and this depends in this vector. So now we can actually use a pseudorandom generator. So instead of generating theta minus 1 random integers ui, we will actually give only the seed of that of a pseudorandom number generator, and that way this lambda to the power 8 we can make it lambda to the power 7.
Don't you need to publish the seed?
Yeah, but the seed will be small.
How do you use the security of pseudorandom generator if you publish the seed?
Yeah, so we assume that that's good.
Well, I mean, some schemes you can actually argue security.
Yeah.
But usually the reason you can argue.
No, but over here we just need like before we are giving these random numbers as public anyway.
Right. So I guess the question is, what do you need to publish here? Do you just need to publish the U1 up to U sub theta, or do you also need to publish the seed?
So instead of publishing U1's like theta random integers U1 UIs, now we publish only the seed and the pseudorandom generator. So it's like we're compressing.
But then you cannot argue that the UIs are random anymore, right? If given the seed.
But if the scheme was secure for random and it becomes insecure for pseudo-random,
But you're giving out the seed.
no, that's only for computation. If you don't give out the seed, take.
Seed is part of the public key, right?
But that doesn't matter, right? Because it's only for.
Like
whatever
before,
property you can
those are
test.
public anyway. Those random, like those UIs.
Yeah, those are public. Yeah,
Those are public.
Fine, that's fine.
Yeah.
But
If I select my numbers instead of randomly, pseudo-randomly,
Right.
the scheme should still be secure.
Fair
See the
enough.
seed.
If the
That's
seed is
fine. You
secret.
cannot see the seed.
Okay.
But I'm not using seed to do anything else. It's only done for selecting the numbers. So seed is just a compression function for this.
So you're saying don't publish the seed.
You can publish a seed. Because seed is not, it's not that you,
But
if you do not publish the seed, you
generator,
agree that the scheme is secure,
Yeah.
right? And now I'm not using the seed anywhere. So you can think of the seed as a distribution function instead of selecting randomly, you're selecting from some different
You're
distribution.
not using it, but the attacker will use it. If you
Yeah.
publish
No, but
it,
you already said that the only reason you're using seed is generating the numbers. Beyond that, you're not using it anymore.
look, how about I'll take a secret key encryption scheme and I use the seed only to expand numbers, and then I'll just publish it as part of the cybertext.
No,
I don't use it for, I don't use it for anything else, I just use it for stats.
Can you decrypt if I give the seed? If you could, then you could.
Of course I can decrypt, it's even better.
No, in this case.
No, like
I don't.
what I mean is like over here, like those random numbers were public anyway, right?
Yes, those numbers are public.
They're not going to be pseudo-random if you see the seed of the pseudo-random generator, right?
Yeah, exactly.
That's the point.
So you're saying that by publishing the seed, there is suddenly some property of the UIs that you can see that will enable you to break?
Well, if you see my talk, right, that we have a counter example, right? So it was like something where instead of random seed, we get pseudo-random seed, we get a counter example.
Yeah.
So I don't see how to do it here. Anyway.
So presumably the argument will go the following way, right? I mean, UIs are random, you assume the scheme is secure. UIs are pseudo-random, if the scheme is insecure, then I can break the pseudo-randomness.
Yeah. Unless there is a combinatorial property. So it's only safe to publish the seed if you can argue some combinatorial property a priori. If you know exactly what property you are trying to protect against, then you can argue with pseudo-random seed this property is likely to hold anyway, and therefore it's safe to publish it because you know exactly what property you're trying to avoid. But if you don't know what property, but I don't know, for the security, what kind of property you're trying to avoid. And if there is a particular set of bad use, then it's fine. But if you kind of don't know what is the set of bad use, then you cannot do it. I mean, usually the rule of thumb is that whenever it's safe to use a PRG, whenever you don't need a PRG. So that's kind of a rule of thumb. So whenever you can have a combinatorial de-randomization, it just might be complicated, you need to use some expander graphs or whatever, then you can use PRG. That's anyway. But anyway.
But I think this one, we are not using it first time, like there was the PKC paper before, over there they were also suggesting doing that. So like this one is not, and our security proof, that's only valid for the somewhat homomorphic scheme. If you are going beyond.
So you're saying this scheme with the squashed stuff, I mean, it doesn't have a proof of security, right? I mean, that's what you're saying.
Yeah, so our security proof was only for the somewhat homomorphic scheme. And after that, we are just arguing heuristically it's secure. Yeah. So so for the decryption circuit, with that hint, what we need is we need to calculate this C star minus this Si, S, and the inner product of S and Z. And due to Gentry and Halevi, they use a trick such that split this theta component secret key in small theta boxes, and such that only one secret key bit inside every box is equal to 1. And that will actually help us to reduce the degree of the decryption circuit. And so in the end, that is what is becoming, we are just making summing B numbers, and only one of them is 0. So this is the picture of the whole decryption circuit. We can forget about this part right now. So this is our S. We have divided in B boxes, and always only one of them over here. We have only one in this vector. So because of that, what happens in the end when you are doing this addition? In this addition, only one component is non-zero, and for that we just do addition statewise. We don't need to think about the carry. And this actually shows But over here in the end, this addition, in this case, this is a full addition. And here we are showing for our parameter, this for this full addition, our degree is 15. And so for Gentry's bootstrapping technique to refresh a ciphertext, we have to publicly evaluate the decryption circuit homomorphically on a ciphertext, and this. But for that, we need the encryption of secret key bits. And we have argued that we have said this theta is lambda cube bits, and each gamma we have lambda to the power 5. So again, we would get the secret key with lambda to the power 8 size. But now we can do again some on the fly computation. That over here that we have seen before this computation. So we don't give this directly. We give and a small like of the square root of size of this thing. So that would make this instead of lambda cube multiplied by lambda to the power 5, we will get lambda to the power 1.5 multiplied by lambda to the power 5. So over here we will get lambda to the 6.5.
So is there anything special about quadratic? So give square root of something. I could.
Yeah, you can do more, but if you do up to quadratic, then you can handle the noise, and if you do more, the noise becomes too large.
So in practice, you're saying quadratic you can handle the noise, but
yeah. In practice, I mean, when you were like implement or not also when you implement, when you are calculating the degree of what will be the degree of all the circuits, like over here we got 15, and those parameters, when you decide the parameters, then you see those are become more.
Who's the best? So you're saying
Quadratic is the best one. So for our security proof, as we said, it was secure under approximate GCD assumption, our somewhat homomorphic scheme, the basic scheme. So in the result before, that one was secure under approximate GCD assumption, and in our case we have error-free approximate GCD assumption. And this says that the approximate GCD assumption says given polynomial many QIP plus epsilon I, that's basically the excise in that we are giving public key. One cannot find P. And for our error-free approximate GCD assumption, we are given this one, and along with one term without any noise. And by looking at tool, looks solving them are equally hard or easy.
But instead of one exact multiple, if I give you 2,
then then we are done. Yeah, but for if we are given just one, then we cannot do anything.
Okay, so one assumption, okay, 2 assumptions. Let me postulate a third assumption where there's Q0P and Q1P without error. Then you're dead because you take the GCD, you get P. That's that. So.
I see your music. So why is approximate there?
So the approximate is because we are given error. So the problem is you are given a bunch of QIP. You know if this error term is not there, you can find the GCD would be P. And given some error, you have to find out the P. So that's the approximate GCD problem.
So you're saying your techniques don't apply well to the error-free version, but not to the original approximate GCD assumption.
No. So with our technique, we cannot prove it secure under this one. We need this assumption. So one of them should be.
Can you break the second one that's factoring? Can you break the second assumption that's factoring?
Yeah, it's seems like, right? Factor.
Yeah.
So is P prime? Was it prime?
Over here, we are taking rough integers as P.
Odd integers, is that right?
Oh,
Yeah.
so then it's not completely clear, but because you could get like product of any numbers in there.
That's kind of interesting because, well, it's not exactly like this, but it's a point of analysis. You cannot break it from factoring. So approximate-GCD, you don't know how to break it as a factor.
No.
But error-free is something you can break it as a factor problem.
It seems like if you choose Q and P to be random, right, from the with 1 over poly probability, they'll both be prime. Right, therefore you factor, you know exactly what P is.
Even if you kind of factor completely Q0 times P, there are maybe like not that many combinations.
But
1 over poly, you know.
Why with 1 over poly you will have both of them prime?
So as 1 over poly, P is prime. If I choose P to be a random odd integer, 1 over poly probability, it's prime. So is Q. Therefore, it's a product.
You just take a prime and then try every possible prime.
So is it anyway related to Schnorr? Because in Schnorr also you get similar terms, right? Except that your P is X. And I published it for X. In this case, I don't publish that, right? So if you look at Schnorr signature, all your signatures are of this form, QIP plus R. Except that you also know GT for QI, you also know GT for P, right?
But why is the I
GT to the power X is your public key, and your response is, I give you GT to the power R, and then your response is X plus, it's a different form, X plus R.
Anyway, epsilon, here's the whole point, is epsilon is short, right?
Small, yeah.
There is no shortness.
So it's small.
If epsilon is as big as P, then it's like a random number, more or less a random number.
Yeah. So here we just briefly see the attacks which we covered. So brute force attack on the noise. It says we just search over all the noise, and for that countermeasure would be takes sufficiently large noise parameter. And next comes the these attacks are based on these attacks. So when we say set our parameters to implement, we say we will base our parameters so that the best attacks we cannot break them our scheme. So the first one was the attack on the noise, and the next one would be the approximate GCD attack. So over here, what we can do is say we have t integers xi of that form, and now we consider a vector u which is orthogonal to xi's. Now, so that means we will have this equation, and if that one is true, we will also have instead of xi we can just put the noise. And if ui is sufficiently small, and because ri is small anyway, the noise parameter using LLL, we can find out u. And then by collecting many orthogonal vectors u, we can recover r. So countermeasure against that would be the size of gamma and xi must be sufficiently large. So what we do is we have plotted, we have applied the best attack against, like these kind of attacks with all security parameters, and then we extrapolate them and try to guess what should be the security parameter we should implement. So, yeah.
Do you guys consider the factoring attack that Sean mentioned? So I try to factor x0 and try to find out p, and that's like the simplest thing you can do, right?
Yeah, but for that I think we are taking.
Asymptotically, it's still slower than because p times q0 is eta to the 4 bits. So factoring it is more than 2 to the eta time, right? Using our field sieve, which is still slower than guessing the noise, which is true data. So symptotically, it seems perhaps okay.
And we are making some numbers like as a rough integers. So the factors will be bigger, so it will be harder.
The opposite is small.
Yeah.
Okay. So actually, what happens if I publish QIs?
If I publish QIs?
Yeah, along with all the numbers?
Well, I divide xi by qi and round it. I get p.
Oh, because the error is too small.
So here this is our implementation results. So we take 4 security parameters, tau, small, medium, and large, as taken by the Gentry-Halevi paper. So for the large, we are aiming for 72 bits of security. So these are the parameters. So what we can see over here for the large scheme, for the key generation, we need 43 minutes, and that actually most of the time it goes guessing making a rough integers. And the encrypt is 3 minutes, expand, and the rest of them are okay except this decrypt, and our public key size is 800 MB. As compared to the Gentry-Halevi implementation, I think over here for the same one they have more than 2 GB, and this is like half an hour. But of course, again, it's hard to compare, and our machines were just a normal PC, and I think they were using much more expensive, like much better hardware. So
rho here is the length of p, and eta is the length of q, right? The bit length of q.
Rho is the noise, right?
Rho is the noise. Oh, sorry.
So how do these parameters, I don't know if you look, I guess, we know the Dijk and others have this new fully homomorphic encryption schemes. I don't know if any implementation was done. How do those parameters compare to the new ones?
We didn't implement the fully homomorphic scheme, so no numbers for this. Sorry? We didn't implement a fully homomorphic scheme. We just implemented the somewhat homomorphic. Yeah, so
at least in theory, well, I don't know. In general, kind of, is it as a comparable, order of magnitude faster, slower? Always hard to tell.
I think it depends. Like when you do the optimizations, you are losing all the security proofs anyway. So then it is. Yeah. So only the somewhat homomorphic scheme is secure, and then. But I guess we can still.
Actually, claims asymptotic performance. It says that you can do all the operations in like any cube type and it's like security parameter. So I don't know what that
much
means.
faster, like it's an RSA, for example.
RSA is also encrypted for a different app.
Right. Oh, I see. Is that cube? He claims it's onto the 6 or something like that.
That's what it is.
Oh, I see. At some point I saw number 6 or 7 in earlier versions of his talk, but now I guess.
So rho, you said rho is the size of the error?
Yeah, rho is the size of the error.
You can get away with having that as 2 to the 39.
That's my everything. So I can break it in time 2 to the 39,
Right,
right?
so it's not 80 bits security.
So it's not 72-bit security, right? Like maybe
Can they really
2
break
times
it?
2 to the 39, but
Wait.
like plus minus, right?
Oh,
So,
yeah.
but,
So, I don't understand this.
Or I think rho is the. No, I think there is some missing. Let me see what I defined before. So.
Right, so if we want 80 bit security, then that row is 80.
Yeah. So this shows that both the lattice-based scheme and the integer-based scheme, both are like, when you implement them, they have comparable performance, and conceptually the integer-based scheme is much simpler. Yeah.
So in the assumption, if the QIs are small, then how does it affect the assumption? Again, you can wait.
If the Q is small,
If the QIs.
then you have a lattice attack.
So then if I'm given the list, and all the QIs are of approximately the same size, if I start subtracting one from the other,
No, but QIs are all large, right? I mean, they're all
but they
more
are
than.
still of the similar size, so the difference will still be small.
What do you mean by small? Right, I mean, I take a 1024-bit number, another 1024-bit number, subtract them, I get a 1024-bit number, right? So they're not small. I mean, they're the same size. I mean, and same holds if you take like many of these.
Yeah, I think that's true, because you can think of the difference as being random. Choose one integer and then add the other one to it.
Sounds good. So, more questions? And I don't want to cut anyone off. Good, okay. Let's thank the speaker again.
Thank you.